The next lesson in Chapter 11 is 11.2, Use Normal Distributions. In this lesson, we'll find yet another way to interpret data. A normal distribution. It says in many large collections of data, scores tend to be symmetrical about a single value that corresponds to the mean, median, and mode. The symmetry can be represented with a normal curve. Please write down the definition of normal distribution and sketch a shape of this curve below. Then press play and we'll fill in the blanks regarding the curve. To create the data in the normal curve, we're going to need two things. We're going to need that single value that corresponds to mean, median, and mode, and we'll define that as x bar. We're also going to need to know the value of the standard deviation. With those two values, we can create our normal distribution curve. Now, right in the middle of those dashes at the bottom, kind of where half of our data falls, right in the middle, that's our x bar. That's where our average or mean would go. Now, the dashes to the right and to the left form a range of values that are standard deviations away. If we go to the left, we're going to subtract one standard deviation. Go to the left again, we'll subtract two standard deviations. And last but not least, we'll subtract three standard deviations. Now your data is getting pretty far away from the mean at that point. Notice the curve is really small. That's an indicator that thing values beyond that would be considered outliers. To complete the normal curve, from our mean, we'll go one to the right, which means we're going to add one standard deviation. Add 2 to the standard deviations. And then last but not least, we'll add 3. Now what this is going to do is give you a range of values in between those dash marks. Now I'm going to take each dash mark and extend it up towards the top of the curve. And we're going to talk about percentage of data values within each of these standard deviations. These are going to be numbers that you are going to want to know. Let's start off with the left side and the right side. That's where the biggest chunk of the data would be, as close to the mean as possible. The percentage here is 34.1% on both sides of the curve, or of that average, I should say. 34.1%. Then between 1 and 2 standard deviations, notice the curve is smaller. The amount of data or percentage of data within that portion of the curve drops all the way down to 13.6. And again, on both sides of the curve. As we get between 2 and 3 standard deviations away, the amount gets even smaller, 2.2% on either side. And last but not least, beyond 3 standard deviations, it's basically flattened at that point in the curve. Only about 0.1% of your data would fall within that category. And likely those would be considered your outliers. Now we can use this information to determine the percentage and probability that an event would occur within one of those standard deviation rules. The last definition we'll use before we start some examples is called percentile rank. You've maybe even heard of this before when you've looked at results from standardized test scores. A percentile rank is the whole number percent up to a data point. Here's how it works. Given a value for x, let's say something like 94.2%. The percentile rank is just the percent up to that amount, the whole number percent. That means at 94.2%, you're at the 94th percentile. Seems easy enough. If you're given 82.9%, here's where we think about rounding, but that isn't going to work for percentile rank. Even if you're at 82.9%, you are at the 82nd percentile. It's always just the percent or the whole number that's closest to, or that goes like up to, the nearest data point. Now, the only time that it defaults to something different is if you're between 0 and 1. If your data point is 0.4% and you're trying to get a percentile rank, even though the whole number out in front is 0, it rounds you up to the first percentile. We can't be at the 0 percentile. That means you wouldn't have taken any, there wouldn't be any data to recognize. Even if you're 1.7, I know it's kind of weird for this part, even 1.7 is at the first percentile. So again, it's always that whole number that's closest up to your percentile kind of without going over, except for when it's 0 and 1. All right, so we'll kind of intersperse finding the standard deviation values along with, the standard deviation values along with finding percentile rank. So down below it says a set of normally distributed data has a mean of 26 and a standard deviation of 4. The nice thing that we're going to use with these normal curve questions is that I'll already give you the 2 data points that you need. We're not going to have to calculate the standard deviation for this. So we'll take that. That's not too bad. All right, so our example says the mean is 26. That's our x bar. And the standard deviation is 4. So over on the right, it says model this with a normal curve. So let's take a look at what I have on the right. Start off by drawing this curve, and there's 1, 2, 3, 4, 5, 6, 7 dashes down below. When we create the data with actual data points versus the definition, x bar in the middle is actually going to be a number. And for us, our mean was 26. Now, if I go to the left, remember we subtracted 1 standard deviation, which means I'm going to take 26 minus 4, which is 22. And then if I go 2 to the left and I subtract 4 again, I get 18. Now all the way at the end, if I go 3 standard deviations to the left, that drops me all the way down to a data value of 14. Let's go ahead and do the same thing on the other side. Instead of subtracting 4, we're now going to add 4. If I go to that first kind of dash right there, 1 standard deviation, that's 30. 2 standard deviations would get us to 34. And then 3 standard deviations brings us all the way up to 38. And there's the breakdown of our normal curve with actual data points. As we look at asking or answering the questions on the left, we have to think about those percentages that we wrote down for the definition of normal curve. Question B, what percentage of the total under the curve lies between 18 and 30? So between 18 and 30, I would have this column in the middle, this other column in the middle, and I would stop. I'd have those 3 columns. Now the percentage that was associated with this column was 13.6. And the 2 tall columns had percentages of 34.1 and another 34.1. So if I want the percentage of the total, which is also known as the percentage of the area under the curve, same thing, we're just going to add those percentages together. 13.6 plus 34.1 plus another 34.1. What percent of data is between 2 standard deviations on the left and 1 on the right? That would give you 81.8%. A lot of your data is that close to the average. I'm going to erase my result in orange on my normal curve, and then we'll talk about question C. Example C, what percentage of values are greater than 18? It was 22, I changed it to 18. Here's why. When we look at the normal curve, if we want values that are greater than 18, my boundary for 18 is over here, way over here on that left, which would mean we would want everything under the curve to that right-hand side. Not impossible to do. We could add all the individual columns using our percentages from our normal curve definition. But if you recall things with complement from chapter 10, we can also apply that rule. So I wanted to show you an example where that could be a possibility. We know that the percentage between 2 and 3 standard deviations was only 2.2%. And even beyond that, that's that 0.1%. But if I want everything but that, we can take 100% of the entire curve and just subtract those 2 out. So 2.2% and that 0.1. Both methods would work whether you add all the columns or subtract out the 2 that we're not including, and we would get a very high percentage. 97.7% of all the data seems to appear to be greater than 18. All right, once again, I'm going to erase the green and we'll try our final example or our final part to this example. Example D, what percentile rank does a value of 30 have? To determine this, let's go to our curve. 30 is one of our values at the x or the x bar plus 1. So I want to know the percentile rank at that location. What we need to do then is determine the area under that curve, or the percentage of values to the left, everything up to that point. So again, we could do one of two things. We can add up all the columns up to 30, or we can subtract from what's left over. If we count up to 30, that would be, let's see, what do we have? We have 0.1 plus 2.2 plus 13.6 plus, where am I at here? Oh yeah, 34.1, sorry, I looked at a different question, plus another 34.1. That's everything up to that curve. If we add all of that together, we're going to be at 84.1%. And a value at 84.1% has a percentile rank of the 84th percentile. Sorry if you can hear all the birds in the background. We just had that big thunderstorm, so now it's sunny and all the birds are enjoying life. Anyway, let's go on to the last example. We're just going to try one more normal curve example. It says the blood cholesterol reading for a group of women are normally distributed with a mean of 172 and a standard deviation of 14. So I'd like you to create the normal curve. Go ahead and draw that out on your paper and see if you can determine the data values for the X bar and then all the values to the right and left. Then determine what percentage of women have a cholesterol reading less than 185. So it would be, 158. It would be up to then that percentile value. About what percentage of women have readings between 158 and 186. And then see if we can analyze about what percent of women have an unsafe cholesterol level in the group if their readings are higher than 200. So take a couple minutes if you would please and complete these tasks. Once you feel you've set up your normal curve and you've answered questions B, C, and D, press play for a quick check and then we're done with lesson 10 or 11.2. All right, everyone, I started with my normal curve on the right, putting 172 in the middle, subtracting the standard deviations on the left, and then adding them on the right. For part B, I said it asks what percentage of women have a cholesterol reading less than 158. So in the green, that would be the kind of the three column values to the left of 158, 13.6 plus 2.2 plus 0.1. And I got 15.9%. Part C, about what percentage of values of women have readings between 158 and 186. Those would be those two standard deviations, one on each side of the mean. Therefore, I added 34.1 to another 34.1. The majority of our data is going to be right around that mean, 68.2%. And then last but not least, readings higher than 200 are considered unsafe. About what percent of women in the group had unsafe cholesterol? 200 would be the two standard deviation values on the very far right-hand side. Thankfully, only 2.3% of women would have fallen within that category. So that's creating a normal curve and interpreting data related to those normal or those key values on the normal curve. So we'll do some work with this with 11.2, and when we get into 11.3, we'll take a look at data values that aren't one of those specific numbers. They're going to be in between somewhere. And we'll be able to evaluate the probability or likeliness we're within that data point and the percentage of values that are up to that data point. So far, that's it for lesson 11.2.